Okay, so till now we have seen the graphs of different quantities. We have seen in the motion that there are various quantities that can be measured, like velocity, time, acceleration, okay, speed, displacement, distance. So these are some quantities that are related, that we have studied in this particular topic. Now we will try to establish relations between these quantities. We will try to derive the relations which relate all these quantities together, okay. And the relation between all these quantities that we studied in motion are known as equations of motion. We call them as equations of motion, okay. The equations of motion, these are something which relates the quantities or all the quantities that we studied till now, okay. They help us to understand the motion of a body, they help us to calculate various aspects or check the various aspects of the motion of a body. Now before understanding these equations of motion, we will consider some assumption. We will take some assumptions, and the assumptions are to establish the relation between the quantities. Our assumption will be, the first assumption is that the body travels in a straight line, okay. The first assumption that we will take is the body is traveling in a straight line. The body is traveling in one dimension. It is not in a plane, it is not in 3D, it's traveling in one dimension, that is on a straight line. It is going only like this, it cannot move like this or move anywhere like this, okay. It can only go in a straight line. We will consider only this situation, that the body travels in a straight line. And the second is, body either travels with uniform velocity or uniform acceleration, okay. That is, either the body can travel with a constant velocity, that is uniform velocity, or it can travel with the uniform acceleration, that is even the speed is getting increased, the velocity is getting increased, but the velocity is increasing or decreasing by the same rate, okay, by a constant number or a constant value. So we will consider only those situations in which the acceleration of the body is uniform, that is a constant acceleration, that is the rate of increase of velocity is constant, okay. Velocity is increasing at a constant rate. So using these two assumptions only, we will try to establish the relation between the different quantities of motion, and we will thus form something which is called as equations of motion, okay. So the quantities, let us first see the quantities that we will consider here. The first quantity that we will consider is t. T denotes the time of motion, okay. That for how much time we are considering the motion, that is denoted by t. Now as I told you initially, that there is something called initial velocity and final velocity. Initial velocity means the velocity at which you first saw an object. It is not necessary that first when you look at an object it is at rest. It might be moving at that time as well, okay. For example, you are walking on a road and you saw a car just passes by you. So when you first saw that car, okay, when you first see that car, that car was already in motion, it was already moving with some speed. Now after that, when you stop seeing the car, okay, the last time when you saw the car, So at that point the velocity of the car can be anything. It may be possible that car stops at that point, or it is moving with some more speed or less speed, so that we will be called as the final velocity. So try to understand the two concepts. Initial velocity means the first time when you saw an object, the traveling with some velocity, that velocity will be called as initial velocity. And what is final velocity? So the last time when you saw an object, okay, when you observe an object for the last time, after that it will disappear from your eyesight, we call it as the final velocity. So the next quantity that is denoted by u represents the initial velocity. So what we call as initial velocity? Velocity of the object. You can remember this in a simple case, that velocity of the object when seen first time. When we see an object for the first time, we call the whatever the velocity with which it is traveling, we call this as initial velocity. And the next term is v, which represents the final velocity. Okay, so this velocity is what? Velocity, okay, velocity of the object, seen for last time. Okay, the last time at which you observed the object will be known as the velocity of the object at that point of time, will be known as the final velocity. Similarly, we have another quantity as s. S represents the displacement. Okay, displacement of the object in time t. Okay, displacement of the object in time t. T means this time, the time for which we are considering the motion, okay, or the time span in which we are observing the motion. And the most important quantity, that is acceleration. Okay, acceleration of the body. So what we are considering is, we are considering that acceleration is constant, acceleration is not increasing or acceleration is not decreasing, it's simply constant. May be possible that this acceleration is positive, or may be possible it is negative, but that do not matter, it has to be constant. Okay, if the speed of the object is decreasing, it should decrease by a constant rate. If it is increasing, it should increase by a constant rate, but the acceleration will not change. Okay, the rate at which speed is increasing or decreasing will not change. Only what will change? The velocity will change by a uniform rate. Okay, so these are some assumptions that we will take before considering the equations of motion, before deriving the relations. Okay, now to derive the relation between these quantities, that is, we have 1, 2, 3, 4 and 5 different quantities. So to derive the relation between these quantities, we will consider the graphical approach. Okay, we will consider the velocity time graph. Using the velocity time graph, we will try to determine how these quantities are related to each other. So here I will write, to establish relation between these quantities, we will consider velocity time graph. Okay. Okay, now, so we said that we are considering only uniformly accelerated motion, and we studied that velocity time graph of a uniformly accelerated body is a straight line, okay, which is inclined at some angle to the horizontal axis. So let's consider a graph like this. This is velocity, sorry, this is time, and this is velocity. Now, what I am considering is, let there is an object which was initially traveling with the speed of u, and after t seconds it is traveling with the speed of v and has an acceleration equals to a, okay, and has traveled a distance s. So let me write here, let a body is initially traveling with speed u and travels a distance s, okay, and travels a distance s in time t, okay, in time t, that is, it is traveling with the, initially it was traveling with the speed u and it has traveled a distance s in time t with an acceleration of a, okay, with an acceleration of a, its speed at time t has become, let's say, v, okay. So consider the situation. I am assuming that a body is traveling with the speed u. It was initially traveling with the speed u. That means when I first saw the body, it was already traveling with the speed u. It was not at rest, okay. This body is traveling with the speed u. It travels a distance s, okay. It is traveling with the speed u and it travels a distance s in time interval t, okay. I am considering time interval t with an acceleration a. Its acceleration is a. It means it is traveling with an acceleration, either its speed is increasing or decreasing. We will consider the speed as increasing, okay. So for simplicity we will take it as increasing and then we will equate it for the decreasing as well. So for time being just assume that velocity is increasing and the acceleration is a positive acceleration. So its speed at time t has become v. So imagine the situation. I was walking on a road and I saw a car passing by. The car was initially traveling with the speed u, okay, and I observed that car till it disappears from my eyes, okay, till it goes to such a way that I cannot see, I am not able to see. Let's say it was traveling in a straight line and suddenly it turned to the right hand side, okay. So I am not able to see because it traveled in some colony, okay. So when I first saw the car, it was traveling with the speed u and I observed it for time t. In that time t, it has traveled the distance s, okay, with an acceleration of a. Its speed is getting increased and with an acceleration of a. And the last time when I saw the car, when it turned in the direction in the right hand side, the last time the speed of the car that I saw was v. It was traveling with the speed of v meters per second, okay. So if I want to plot the graph of this situation at time t is equals to 0, I will say velocity is u, because as I said the initial velocity is u. So first time when I saw the object is t is equals to 0, so let's say the velocity of the object is u. This is the velocity of the object, and after t seconds, let's say at somewhere here at t seconds the velocity of the object becomes v. So if I mark this point like this, this is the position of the car after t seconds. This was the initial position of the car, and let us draw the line, let us join these two lines. Like this, and this is, let's say, angle theta. So tan theta, that is the slope of this line, will give you the acceleration, which is equals to a. Acceleration will be equals to a. Now observe the situation. This point is at t is equals to 0 and this point is at t. Initially the velocity is u and finally the velocity is v. You can see this. So what we can see from this graph, the slope will give you the acceleration as we studied previously, okay, and in this case let's say this point is A, this point is B, this point is C, this point is D, this point is E, and this is, let us say, F. So what I can say in this graph, the slope of this line will be equals to BC upon DC, okay, that is BC upon DC. BC upon DC will give you the slope of this graph. Now what is BC? If I ask you BC, you can see B point is V, C point is U. So BC will be equals to V minus U. That means from this if I subtract this part, I will get this part. So slope, that is A, is equals to BC, which is V minus U upon now DC. DC means time interval from this point to this point. This is equal to T. So A is equals to V minus U upon T. Now transfer this A to the LHS, it will give you AT is equals to V minus U, and from this I will get V is equals to U plus AT. This is known as first equation of motion. We call this condition, we call this relation as the first equation of motion, and this is an equation which shows the relation between velocity and time. Okay, so this is the curve, this is the equation or relation of velocity and time. Okay, we know that there is acceleration as well, but we say that this relation is the relation between velocity and time. We call this as first equation of motion. It's very, very important condition. Okay, so this is how you have to derive the relation. So this is the first relation that we have derived, that is the first equation of motion. We have two more equations of motion which can be derived using the same graph. Okay, so first you note this condition and then we will derive the second and third equations. Okay, so we have derived the first equation. So let's write here. First equation is V is equals to U plus AT. Okay, so V is equals to U plus AT is the very first equation of motion. Now, secondly, we can derive the second equation of motion. Let's see how. Using this velocity time graph, we know a condition that the area inside the velocity time graph gives you the distance. Okay, so the body has traveled from t is equals to 0 to this t point. I can say the distance traveled by the body in this t time is the area of this region. Okay, the area of this region represents the distance traveled by the body in time t. So the distance traveled by body in time t will be equals to, you can see, area of this particular region. This region is DBEF. Okay, so this region is D, or we can say area of DBEF. So the distance traveled in this t interval, in this t time, is DBEF. Okay, so this is the area of region. Now we have seen that in the condition what we have assumed, that during this t time the body has traveled s distance. You can see where it is, this is. So in this t time, in this t duration, I can say the body has traveled s distance. It means this distance is equals to s. So here I can write s will be equals to area of DBEF. Okay, so s is the distance traveled in this t time interval. So this is equals to area of DBEF. Now we can see DBEF is formed by two figures. One is this triangle, okay, and another is this rectangle. So I can say area of DBEF, instead of it I can write area of triangle, this is DBC, plus area of the square DCEF. Okay. Now what is the area of triangle DBC? It will be equals to half into base. What is the base of triangle DBC? It is DC. DC is the base, and what is the height? Height is BC. So here I can write half into base is DC into height is BC. So half into base into height represents the area of triangle. Now what is the area of this rectangle? Area of rectangle will be length into breadth, that is DC into CE, okay, or you can say FE into DF. So this will represent the area of rectangle is FE into DF. FE into DF. Now what is BC? BC is V minus U, okay. From this V, if I subtract U, I will get BC. So in place of BC I can write, half into, and in place of DC is T, in place of BC I can write V minus U, okay. Now plus FE is again T into what is DF. Observe the DF, you can see it is U. This is the DF. This is U, this is FE, which is T, DC is also T, while this BC will represent U minus V, okay. So we got this condition. Now let's simplify this condition. Now I can multiply this T and half in the bracket. So what I will get is half into V into T minus half into U into T, plus here I will get U into T, okay. Now using this condition I can see half into Vt, and this is minus half into Ut. So let's write it like this, or instead of multiplying what we will do, let's solve it here only instead of multiplication. We have this condition, okay. Now we write it in this way, U into T plus half times V minus U into T. Now what is V minus U? V minus U, what is V minus U? Here we have seen that acceleration is equals to V minus U upon T. So from this what I can see, V minus U is basically equals to A into T, okay. So in place of V minus U I can substitute A into T. So what we will get is Ut plus half, and in place of V minus U I will write AT into T. So observe the equation, observe the condition. In place of V minus U I substituted AT, and we will get S is equals to Ut plus half. Now A will come as it is, and then this is T, okay. In place of T into T, what we will get? T into T will give you T square. So here I can write T square. So our condition becomes S is equals to Ut plus half A T square, and we call this condition as the second equation of motion, okay. We call this condition as the second equation of motion. It represents a relation between distance and time, okay. So it's a distance time relation. It will give you the relation between distance and time, that is distance time relation, okay. So in this way we can derive the second equation of motion. Now so using this second equation of motion we can derive the third condition as well, the third equation of motion as well. Let's see how we can derive. See, we have this condition, this one, that is ut plus half v minus u into t. So let's use this condition. So from here what we have is s is equals to half of v minus u into t plus ut. Simplify this condition, half v into t minus half u into t plus u into t. This is equals to s. Okay. What I did is I simply used this condition. So here what I can see, s is equals to half vt will come as it is, half v into t will come as it is. This is minus half ut and plus ut. So this will give you plus half ut. Just solve these two conditions. Okay. Minus half ut plus ut will give you half u into t. Now from this, if I take t as common, so I will get half and t as common, so half then v plus u. I will get this condition, half t into v plus u. Okay, s is equals to this. Now from this, if I transfer this 2 to this LHS, I will get 2s is equals to t times v plus u. Now observe this condition. From this condition, if I calculate the value of t, how will you calculate the value of t? Using this, let's use this condition. The value of t can be calculated by substituting or by replacing t and a. Okay. If I interchange the position of t and a, t will become v minus u upon a. Okay. T will become v minus u upon a. Now I will use this t is equals to v minus u upon a here, and this will give you 2s is equals to v minus u into v plus u will come as it is upon a. Okay, v minus u into v plus u upon a. Now this condition can be solved as, just transfer this a from this denominator to LHS, you will get 2as is equals to v minus u into v plus u. Now what is v minus u into v plus u? This is equals to v square minus u square, that is a minus b into a plus b will give you a square minus b square. In similar manner this will give you 2as बराबर v square minus u square. Okay, तो यहाँ से हमें पता चलेगा कि 2as बराबर कितना होगा, v square minus u square, and this is known as the third equation of motion. We call this equation as the third equation of motion, and it is also known as relation between velocity and distance. Okay, that is distance velocity relationship, it is also known as in this manner, and we call this as the third equation of motion. Okay, so these are the three equations of motion. This is the first equation of motion, v is equals to u plus at. Okay, this is the second equation of motion, s is equals to ut plus half at square, and this is the third equation of motion, 2as is equals to v square minus u square. Okay, so these are the three important equations of motion. So first you note this, then we will see how some special cases can be applied on these three equations of motion. Okay, so first note this. Okay, so we have derived the three equations of motion. Okay, now as I told you, these equations of motion are very important in calculating various parameters. So for that, let's see some special cases, that how to apply these equations of motion. Okay, so for the first case we will assume a general case, case 1. The case 1 is when the body, when the acceleration of body is in the direction of motion. Okay, So first case will be when the acceleration of the body is in the direction of motion, that is acceleration and velocity both are moving in the same direction, both are in the same direction. Okay. So here I will say acceleration and velocity both will have the same direction, that is acceleration will be positive. So we will say here acceleration is positive. Now when the acceleration is positive and it is the body is moving in single direction, that is in a straight line, and acceleration is also in the same direction, it means the velocity of the body is increasing. Okay, and here for this case the equations of motion will become v is equals to u plus at, s is equals to ut plus half at square, and 2as will be equals to v square minus u square. Okay, that means there is no change in the equations of motion when we consider a very simple case that the acceleration is in the same direction as the motion, as the direction of motion. Okay, but when the situation changes, okay, consider case 2. When acceleration is opposite to the direction of motion. Okay, what will happen when acceleration is in the opposite direction of motion, that is the direction of acceleration and direction of velocity are opposite. So in this case we will say that acceleration is negative, or we say that acceleration is retardation. Okay, we say in this case we have the retardation instead of acceleration. So how the equations of motion will going to change? You can see in the situation where we have acceleration as a, all the places, in every place the acceleration will become negative, that is the a will be replaced by minus a. Okay, so case 2, when the acceleration is in opposite direction to the motion of the direction of motion, a is replaced by minus a. So in this case the equations of motion will become v is equals to u minus at, s is equals to ut minus half at square, and minus 2as is equals to v square minus u square. Okay, so these are the three conditions for retardation or the negative acceleration. These are the three conditions for the positive acceleration. Okay, now consider case 3. Case 3 is when the body is initially at rest. Okay, now when the body is initially at rest, it means when you first saw the body it was at rest, after that it starts moving. So it means when you first saw the body when it was at rest, it means the initial velocity u will become 0. Okay, the condition is that initial velocity u will become 0 when the body is initially at rest. Okay, so how the equations of motion will going to change? You can see in all these three equations, in place of u we will put a 0. Okay, in place of u we will put a 0. So first equation of motion, which is v is equals to u plus at, this will become 0, and we can write v is equals to 0 plus at, that is v is equals to at, and s is equals to ut, that is 0 into t plus half at square. This will become s is equals to, now 0 into t will give you 0, so s will become half a t square. Okay, now in the third equation it is 2as is equals to v square minus 0 square, and this will give you, what will happen with this 0? It can be neglected, so 2as will become v square. So these three will become the equation of motion when we have zero initial velocity, that is when we have the body initially at rest. Okay, so these three will become the equations of motion. Now consider the case 4. Case 4 is when the body stops finally. Okay, now this is a very typical case when the body stops finally. See, when the body is moving with some velocity and it is getting stopped finally, we are considering only those cases in which we have a uniform acceleration, either uniform positive acceleration or either uniform negative acceleration. It means if a body is traveling with some speed and finally it stops, then definitely it do not stop suddenly. Gradually its speed is going to be decreased, and finally after a decrease in velocity, after a decrease in speed, it will going to stop. So in this case what you will find that the final velocity of the body v will be equals to 0. Okay, but is this the only situation or that v is 0? No, there has to be something more, because the velocity of the body is becoming 0 finally. It means in this case acceleration is negative. In this case acceleration is definitely in the opposite direction to the final or to the velocity or to the direction of motion. In that case only the velocity will going to be 0 finally, because we are simply considering the case of uniformly accelerated motion. So here we will say acceleration will be negative. So what will happen? If final velocity is 0, acceleration a can be replaced by minus a. So how will this equations of motion look like? We have this v is equals to u plus at. Okay, now in this equation what will happen? We will replace v by 0, u will remain as it is, and what is a? A will become minus a, and t will remain as it is. Okay, so v equals to u plus at will become 0 is equals to u minus at, and this will going to become u is equals to at. Okay, this will going to become u is equals to at, the situation in which we have 0 final velocity and a negative acceleration. Now consider the second equation, s is equals to ut plus half at square. What will happen in this equation? Okay, what will happen in this equation? You can see here s will remain as it is, u will remain as it is, t will remain as it is, and minus half a t square. Okay, so the equation will become s is equals to ut minus half a t square. And how the third equation will going to change? So this is the second equation, and how the third equation will going to change? It is v square minus u square is equals to 2as, and this will become, in place of v square I can write 0 square minus u square is equals to minus 2, then this is a will become a negative, that is minus a and s. So when you solve this, it will come out to be u square is equals to 2as, and this will be, and this will show you the relation between u square and a and s. So the equations will change to this form. Okay, when the body finally stops, when a body is moving, for example I throw a ball like this, the ball will start moving with some velocity, and in the air at some point it will going to stop. So in this situation what I can say, initially the ball has some velocity, but finally the ball has 0 velocity. Okay, so in that case we will see that equations of motion will become something like this. Okay, here we can see the acceleration. Okay, acceleration is constant, acceleration will not going to change. We are considering such a case where acceleration is not going to change. Okay, and t represents the time period in which I am considering. Okay, so in this way we can modify the equations of motion and we can get some important results out of it, which helps us to solve the questions, which helps us to solve the numerical problems. Okay, so you can note this and then we will continue.